Okay, hello. In the second part of lecture 14, I'm going to proceed with the properties of modulation. Okay, in properties of modulation, which we can refer to the attachment here. Okay, you can refer to this attachment, the first page where we have a modulation properties here. Okay, so we have these terms here where if we have xt multiplied with the sine omega t, the Laplace transform is written to be look like this. And if we have modulation xt multiplied with the cosine omega t, the Laplace transform can be written to be look like this. Okay, modulation means that it's a multiplication of the time domain function xt with either sine omega t or cos omega t. Okay. Next properties is a convolution. Okay. If we have in time domain ht equals to ft mod convolve with the gt, yeah, so this is a symbol of convolution. So in Laplace transformation, ht is now returned to bhs, and this modulation value or modulation operation in time domain will be transformed into just a multiplication in frequency domain. Yeah, so we have ft is fs, Laplace transform of it, and gt is transformed to gs. So in frequency domain or Laplace transform, it is simply fs multiplied with the gs. So we have these properties. Yeah, it's a convolution. Yeah. Okay, so let's have a look at this example here, which is to find a self-convolution for xt. What is meant by self-convolution? It's mean convolution between xt and xt, in which xt is given to be ut minus 1. Okay, so let's have a look at the solution for this example. Okay, so we are given this xt, which is ut minus 1. Okay, so self-convolution means xt convolve with the xt, which means this is a ut minus 1 convolve with ut minus 1. So what we have to do now is that we're going to transform this into a Laplace transform. So in Laplace transform, in time domain, it is convolution. So in frequency domain, it's multiplication, which is xs multiplied with xs. So we're going to have, so this term shall be now converted or transformed into Laplace transform. So we have ut will be 1 over s, ut minus 1. So we're going to apply the time shifting property, so that will give us 1 over s exponential of negative s. Okay, so here's a multiplication, yeah, in frequency domain. So when we do a multiplication, we're going to have 1 over s squared minus 2 over s squared e minus s plus 1 over s squared e minus 2s. Yeah. Okay, so in order for us to find the results of this self-convolution, so what we have to do is that we have to do an inverse of Laplace transform. So you can refer to the table, yeah, where we have 1 over s squared. Yeah, so refer back to this table. Yeah. Okay, let's proceed with page 2 here. So if we have, I'm referring to signal number 5. So Tn ut will be n, yeah, over s over n plus 1. So if we have n equals to 2, so this will give us 2 over, sorry, if we have Tn equals to 1, we're going to have a 1 over s to the power of 2. So that's why we have here, sorry, if we have 1 over s squared, its respective time domain, it will be t of ut, yeah? So t of ut, when we do a Laplace transform, it will give us 1 over s squared. Okay, the same thing is applied for the second terms in frequency domain, where we have 2 over s squared e minus s. So remember that here we have exponential negative s, means that in time domain, it should be a time shifting. So that's why we can write this as simply 2 of t minus 1 of ut minus 1. And likewise, for the third terms here, we have exponential of negative 2s, means that we have a time shifting by 2 units. So we have t minus 2 of ut minus 2. Yeah. Okay, I hope that you are clear about this inverse of Laplace transform. So again, if you have any question on this, kindly please contact me, yeah, through WhatsApp or any medium of communication. Okay, let's proceed with the next examples. Okay, so we are given these examples. We are given a LTI system as shown in figure 3b, where we have the xt is a rectangular structure having a duration from negative half to positive half, yeah, negative half to positive half, yeah, with the amplitude of 1. And the xt signal is now the input to the system of h1t, and the output is y1t. We are further given that h1t, the system's equation, is equals to xt plus 2, yeah? Means that h1t and xt are interrelated. We can have a relationship between xt and h1t. Okay, so the question is, by using the properties of Laplace transform, determine the mathematical expression of y1s and y1t. It means that we have to find the y1t or y1s, yeah? Okay, so let's have a look at the solution for this example. Okay, so we can write, this will be the block for relationship between xt, h1t, and y1t. Okay, so please bear in mind, yeah, students, if you are given this block, relationship in time domain between the input, the system's equation, and the output supposedly must be y1t is equals to xt convolved with h1t. Okay, so this is convolution in time domain, yeah? So this particular block states that relationship between the input, the system's equation, and the output is a convolution. y1t is xt convolved with h1t. Okay, so this is the graph, I mean the signals which is obtained from the given question. So the question states that this is the xt, while the h1t is given to be xt plus 2. Yeah, I go back to the question just now. Okay, we have h1t is xt plus 2. Yeah, so that's why we have xt is this, and h1t is this terms, where h1t is basically xt which has been shifted by 2 units to the left. Yeah. Okay, so this should be the relationship that I've mentioned just now. So what we have to do now is that we have to do the Laplace transformation. So in Laplace transform, we're going to have y1s shall be equals to xs multiply with h1s. Yeah, because the time domain, a convolution in time domain will result in multiplication in frequency domain. Okay, so let's find xs and h1s from its respective time domain signal. Okay, so we know that for the xt, it can be written in terms of the step unit function. So we have ut plus half minus ut minus half. So the Laplace transform will be xs will be equals to 1 over s exponential s over 2 minus 1 over s exponential negative s over 2, which is based on the time shifting properties. Likewise, for h1t, it is ut plus 7 over 2 minus ut plus 5 over 2. So in Laplace transform, we are going to have h1s of 1 over s exponential of 7s over 2 minus 1 over s exponential 5s over 2. Yeah, so these xs and h1s will be multiplied. Yeah, so we're going to have this multiplication, and when we multiply these two xs and h1s, we are supposed to get these terms here. We have 1 over s squared exponential 4s, 1 over s squared exponential 3s, minus 1 over s squared exponential 3s, plus 1 over s squared exponential 2s, which is simplified in these equations down here. Okay, remember what's the task? The task is to find the y1s and also the y1t, which is the inverse Laplace of y1s, yeah? So from here, we're going to have y1s should be y1t. Okay, sorry, this is supposed to be an inverse Laplace, yeah? Not Laplace transform, it should be inverse of Laplace transform. Okay, please correct this for me. This is even Laplace transform. So basically, this will involve, since we have 1 over s squared exponential for s, so we know that the functions that is involved here will be tut, and because we have exponential for s, it will then consider the use of a time shifting property. So we have t plus 4, ut plus 4. The second terms, again, we're going to have 2, t plus 3, ut plus 3. And the third term should be t plus 2, ut plus 2. Okay, so this is the results, the answer for examples, yeah? Okay, let's proceed with the next properties. So this is properties of differentiation. Yeah, differentiation, which states that if we have n order of differentiation of ft, yeah, so the Laplace transform, this will be s power of n fs minus blah 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 blah. Okay, just to remind you that our concern is only up to the second order of differentiation, which if ft, the Laplace transform is fs, so if ft is said to be differentiated for the first time, which is first order differentiation, so its Laplace transform will be s multiplied with fs minus f0. So f0 here means this is a time domain value, ft, when t equals to 0. Yeah, so I repeat again, f0 here means this is ft, a time domain signal value when t equals to 0. So this is written to be f0, yeah? Whereas for the second order differentiation, d squared ft over dt squared, so based on these equations, we can have for the second order differentiation, it should give us s power of 2 of fs minus s of f0, which is same f0 of this, yeah, which is the time domain value of ft when t equals to 0, minus df0 over dt. So this is mean by the value of first order differentiation in time domain, yeah, dft over dt, okay, when the value of t equals to 0, okay, all right. I hope it's clear, yeah? This is the value of ft when t equals to 0. This is the value of dft over dt, yeah, dft over dt when t equals to 0. Okay, so our concern is only up to the second order of differentiation in time domain, yeah? Okay, so let's have a look at these examples. Okay, so we are given y double prime t, so this is a second order differentiation, y double prime t plus 6y prime t is order differentiation, plus 5 of yt equals to 2. So we are given further that the value of yt when t equals to 0 is 1, and the value of dyt over dt when t equals to 0 is negative 3. Okay, so I hope you understand here, yeah? So this is the value of time domain function, yt when t equals to 0. This is the value of time domain function, dyt over dt when t equals to 0. So based on this equation and based on this information, you are requested to find the yt. Okay, so we need to use the properties of differentiation to solve for this example. So let's have a look at the solution to these examples. Okay, I'm going back. This is the solution supposedly. Right, so what we have to do is that we have to transform the left and right side of these equations in time domain to a frequency domain. So by using the properties of differentiation for the du squared yt over dt squared, which is the second order differentiation, we're supposed to get this, yeah, s squared ys minus sy0 minus y prime 0. Okay, you can refer back to the equation that we have learned in the lecture slide just now. Second order differentiation, sorry, first order differentiation, second terms, we are supposed to get 6. Okay, so the inner side here is the Laplace transform for y prime t. So we have s ys minus y0. Yeah, and the third term, 5yt will give us 5 of ys, and 2 will give us 2 over s. So y2 is 2s, so 2 is considered to be a step, a constant value. So when you have 2 as a step function, which is 2ut, so we're going to have the 2 over s as the Laplace transform. Yeah, so this 2 is considered to be 2 of ut. Yeah, 2 of ut. Laplace transform will give us 2 over s. Okay, so next we're going to substitute all the values given, which is y0 equals to 1, y prime 0 equals to negative 3. We're going to substitute these two values in these equations. So we are supposed to get this, yeah, y0 is 1, y prime 0 is negative 3, y0 is 1. So we're going to rework for these equations. So end up, we are supposed to get these equations here, ys s squared plus 6s plus 5 equals to 2 over s plus 3. Yeah. Okay. So we rearrange the equations here. We are supposed to get s squared plus 3s plus 2 divided by s multiplied with s squared plus 6s plus 5. Okay, so this is where you need to apply the partial fraction. Okay, so partial fraction has been done, right, in lecture 13. So this is where we have to use it. So what we have to do now is that we have to factorize this denominator term. So factorize, we're going to have s plus 1, s plus 5. So these equations, these terms basically can be written in partial fraction to be a over s plus b over s plus 1 plus c over s plus 5. So your task is to work out for the a, b, and c, and then only we can find the inverse of Laplace transform to get the yt. Okay, so that's the idea, yeah? Okay, so in this example, I'm very generous to give you the answer to work for A, B, and C. So to find A, let us proceed with the partial fraction topics that we have learned in previous slide or previous lecture 13. So to find A, what we have to do is that we have to multiply both sides of left and right with S. So we're going to get left hand side will be s squared plus 3s plus 2 over s plus 1, s plus 5 because s has been cancelled out. Whereas for the right hand side, we're going to have these terms here. Okay, so to find for A, what you have to do is that we have to substitute s to be 0 for left and right. So end up when we substitute A, so when we substitute s to be 0, so your A value shall be equals to 2 over 5. Okay? So likewise, to find B, yeah, from this equation, to find B, we have to multiply both sides with s plus 1, so that we're going to have B only on the right-hand side, yeah? So that's the idea. So when you multiply both sides with s plus 1, left-hand side, we're going to have this, right-hand side, we're going to have this. So to find B, you have to substitute the value of s to be equals to negative 1, such that you're going to have B equal to 0. Okay, and finally, to find C, the same methods is to be used, which is to multiply both sides with s plus 5. So work out for that, we're going to have s squared plus 3s over 2 over s plus 1. And for right hand side, we're going to have c plus a and b terms here. So to find c, simply we substitute s to be equals to negative 5. So end up your c should be equals to 3 over 5, yeah? Okay, so we have find the A and C because B is 0. So simply your ys will be 2 over 5s plus, so I have to go back to C. So 3 over 5s plus 5. B is 0. So since you have ys, you have obtained the ys successfully, I believe that you can find the inverse Laplace transform to find the yt. Yeah. So, but if you get problems with this inverse of Laplace transform, kindly please contact me. But I believe that up to now, you have now understood very well on the inverse of Laplace transform. Yeah. Okay. Right. Okay, I'm going to stop here. So in part 3 of lecture 14, we are going to proceed with the integration properties. Yeah. Okay, so thank you very much and see you then.